Lesson 2 of Chapter 2 is on polynomial functions. So as you know, the prefix poly means many, and so a polynomial function has a fairly difficult definition to decipher through. This is an example of a polynomial function with its theory, and really the important thing to understand is that the exponents have to be non-negative integers. Okay, so you can't have any negative exponents and you can't have any exponents that are not integers. All right? So keeping that in mind, polynomials have degrees. You can see these three pictures. If the degree is 0, it's just a constant function. If the degree is 1, it's a linear function. If the degree is 2, it's a quadratic. And it can keep going up to degree 3, 4, 5, etc. So those are some examples of polynomials. Now, if you look at this picture on the left, this is an example of a polynomial function. Polynomials are always continuous functions, and they never have any sharp edges to them. They're always rounded and continuous. Okay? The example here in the middle would be an example that's not a polynomial because it's broken apart. And then the example here on the right would not be a polynomial because it's got a sharp corner to it. So the first thing we're going to do is we're going to talk about end behavior. We've been doing this for a few weeks now. And the end behavior of this particular function can be determined without even looking at the graph. So if we look at the degree, which is simply the largest exponent, we can see that the degree is 4. If it's a fourth degree polynomial, then we know that both ends are going up or both ends are going down. Since the leading coefficient is a positive 3, so again, this is what I'm focused on, then we know that it's going to have both ends going up. Thus, the limit as you go to the left is going up, and the limit as you go to the right is also going up. If we now check this by looking at its graph, we can see that both ends do go up, and so we did describe the end behavior correctly. The directions say explain your reasoning using the leading term test. Well, the leading term test is just focused on the largest exponent and the leading coefficient. Next one, describing the end behavior. The mistake that a lot of people make is they just look at the first term and they would say that this is a second degree polynomial and the leading coefficient is -3, but actually this is a 7th degree polynomial with a leading coefficient of a -2. Therefore, since it's an odd degree, the ends will go in opposite directions. And since the leading coefficient is a -2, as you go to the left, it's going to go up. And as you go to the right, it's going to go down. And you can see the picture of the graph does in fact have the left side going up and the right side going down. So one more example here. If we look at this function, we can see that we've got an odd degree polynomial, which means the ends will be going in opposite directions. And since the leading coefficient is a +1, as we go to the left, it's going to go down. And as we go to the right, it's going to go up. If we take a look at its graph, sure enough, we see the left side going down and the right side going up. Now, the next thing I want to talk to you about is some examples. The pictures on the left are cubics, which means that they're third degree polynomials. Well, the picture here on the left has 3 zeros, or x-intercepts, 1, 2, and 3. Okay? The picture right next to it, another cubic, only has 1 0. So here's the rule. If it's a third degree polynomial, it can have up to 3 possible real zeros. But it doesn't have to have 3 zeros. It may only have 1 real zero, like the picture you see circled in green, which means that the other zeros would be imaginary zeros. And we'll talk more about that soon enough. Next, once you look at the pictures on the right, these are quartic functions, or fourth degree polynomials. On this particular picture, you can see that there are 2 zeros, or x-intercepts. But the picture on the right has 4 zeros, or x-intercepts. So the rule is that every fourth degree polynomial can have up to 4 possible real zeros. but they don't have to have 4 real zeros. The graph circled in black obviously has 2 real zeros, which means that the other zeros are imaginary, which again we'll get to. The other thing I want to talk about is the turning points. If you take a look at the graph circled in red, this is a third-degree polynomial, and it has 2 turning points. But the graph circled in green is a third-degree polynomial with no turning points. So the rule on turning points is that it can have up to 1 less than the degree of possible turning points. So here's the kind of examples you're going to have. It's going to give you a function like this, and as we look at this function, we can see it's a third-degree polynomial, which means that the ends will be going in opposite directions. And since the leading coefficient is a positive 1, it's going to have the right side going up and the left side going down. The problem says to state the number of possible real zeros. Well, since it's a third degree, there's 3 possible real zeros. And since it's a third degree, there's 2 possible turning points. It says then determine all the real zeros by factoring it. So I'm going to take this expression, I'm going to set it equal to 0, and then I'm going to factor it. We can take an x out of everything. We call that the GCF, greatest common factor. This gives us a trinomial that we can break down, and we can factor that into x minus 2 and x minus 3. Thus, now that we have it in a factored form, we can see that the zeros are 0, 2, and 3. And so when we look at the graph, we should see 3 x-intercepts, and we should see what I call a discal guy Randy. Okay, sure enough, we can see it crossing the x-axis at 0, 2, and 3. Here's another example of the same kind of problem. This equation right here is a 4th degree polynomial, which means that there are 4 possible zeros, 4 possible real zeros, and then that there are 3 possible turning points. We'll take a look at the graph in just a second. Now we're going to have to determine the real zeros by factoring. So if we take this equation, set it equal to 0. Now this one gets factored a little bit differently. If you notice the exponents, they go from 4 to 2 to 0. So we can factor this like a quadratic, but we need to have an x squared at the beginning of both binomials because x squared times x squared gives us x to the 4th. Now we need 2 numbers that multiply to give us positive 15, add up to give us negative 8. So that would be negative 5 and negative 3. So we have it factored. Now if we set each factor equal to 0, we're going to get x equals plus or minus the square root of 3. And we're also going to get x equals plus or minus the square root of 5. So looks like we're getting 4 real zeros. And if we take a look at its graph, we have square root of 3 is roughly 1.7. That's this one right here. And then obviously negative 1.7. And then the square root of 5 is like 2.15 roughly. And that's these 2 x-intercepts.